Hello everyone, I am Safi Shahbazi, and as an assignment of my CSE320 course on data communications, I've prepared this video presentation. And in this, what I'm going to explain to you is Pure ALOHA, which is a type of random access protocol. Well, these terms might seem a little vague and highbrow to those of us not familiar with this field. So what we can do is we can start a little basic. First, we'll know about multiple access protocols. And for that, we need to visualize how data is transferred in today's world. As we know, networks may have countless devices, depending on the type of network, of course. For example, multiple devices in your room itself, such as your phone, your laptop, your PC, or your PlayStation, they require to send and receive data. So it is only practical that all these devices have to share channels or mediums to exchange data. So what can happen while sharing a channel is, let's have a look. Suppose these three devices want to share a channel to send their data. So when all three of them want to share a single channel simultaneously, what happens is, boom, data coming from the three channels collide and become corrupted. As a result, they need to be retransmitted. This problem is solved by multiple access protocols. These are some protocols maintained by networks and devices which ensures successful transmission of data. And a type of multiple access protocol is random access protocol. Random access protocols work such that the sender devices have no communication between them. Each device is independent and not controlled by any other. They just send the data randomly and on basis of their own protocols. Now, the first and most basic type of random access protocol is Pure ALOHA. Let's know a little about its origins. In the 1970s, Pure ALOHA originated from a project known as ALOHANet at the University of Hawaii. Its primary goal was to facilitate transmission of data in terms of packets over wireless signals and across the Hawaiian Islands. Now, let's take a look at how Pure ALOHA works. Let's say this network system is following Pure ALOHA protocol. And as we already know, in case of random access protocols, the senders do not communicate with each other. So before sending a data, they don't know whether the channel is occupied or not. Let's take a look at this example. This space indicates a span of time in a time frame. Let's suppose the time span starts from 10 o'clock and with increasing seconds, we move rightwards. Now, one of the senders, let's say station 1, decides to send a frame of data at 5 seconds past 10 o'clock, but station 1 is completely oblivious to what is happening in the data channel, whether there is a pre-existing data frame or not. The sender just randomly sends the data regardless. Here, it is important to note that a channel cannot have more than one data frame at a time. And for this example, we suppose each frame takes 10 seconds to traverse the channel. So station 1 does its job by sending the data and is happy. What it doesn't know is that station 2 had already dispatched a data frame 5 seconds ago at 10 o'clock. This means as all data frames take 10 seconds to traverse the channel, there will be 2 data frames in the channel at 5 seconds past 10. That means at this point. This results in collision. To have a clearer idea, let's look at this slide. Here, frame 2.1 is traveling through the channel, and while the frame is not fully through to the receiver's end, frame 1.1 jumps into the channel. This results in collision and thus corrupts the data. Again, apart from not knowing if anyone precedes it, a station also doesn't know whether or not anyone succeeds it. What if station 4 decides to send data at 13 seconds past 10? Then there will be another collision. Well, there might be some lucky senders who do not collide with anyone's time slot. Frame 3.1 seems lucky here. But then again, what if station 2 decides to send another data at 33 seconds past 10? Another collision. Unlucky. So then, when and how is it safe for a station to send its data? Let's look at this example. Station 1 decides to send some data at 15 seconds past 10. And this time, luckily, frame 1 looks all safe and good to go. So can we say that a data frame is good to go if no other data frame enters the channel during its time slot? As in, no one should enter the channel from 15 seconds past 10 to 25 seconds past 10? It might look like the case, but it's not. What if a data frame enters the channel at 10 seconds past 10 before frame 1.1 even started its journey? They will still collide. Therefore, it is safe for the data frame only if the channel is empty from 10 seconds before its entry. So, if TFR is the transmission time of a frame, for a successful transmission, the channel has to be empty from 10 seconds before its entry. In other words, the channel has to be free for 2 TFR seconds. Since there is a risk of collision if any other frame is present at the channel during this 2 TFR period, it is called the vulnerable time of a data frame. But how is this issue solved? In Pure ALOHA protocol, for any data being sent by a sender, it gets an acknowledgement reply from its receiver. So after dispatching the data, the sender waits for twice its propagation time to receive the reply. So if there is collision in the channel, the sender does not get any acknowledgement message even after waiting for twice the transmission time. So after waiting for twice the transmission time, the sender waits for a further random period of time and then sends the data again. It keeps repeating the process until the transmission is successful. But what will happen if there is a traffic blockage or a broken link in the channel? The sender will never receive a word back from the receiver and will keep repeating the process up to infinite recursions. Let's look at this pseudocode. So what's happening here is a station has decided to send a frame, and when it's trying to send it for the first time, a variable named k gets initialized. That means the checking factor for each iteration of the loop will be k. So when k reaches k max, it will stop looping and abort the mission. And this value of k is generally 15. So what's happening here is the sender is sending the frame and waiting for twice the transmission time of the frame. And if by that time an acknowledgement is received, then the mission is a success. But if not, then they choose to wait for a random period of time and start the process again. Trying likewise, if even after 15 trials, if the station doesn't receive a reply, then it decides to abort the mission. Now, there's this limitation in case of Pure ALOHA, that each data frame occupies twice or more of its transmission time to successfully transmit the data. How to deal with this inefficiency? Just then, slotted ALOHA comes to the rescue. It deals with the excessive time consumption issue of Pure ALOHA, but that's for some other time. And so, that should be it for this one. Thank you for bearing with me. I really hope all your questions and confusions about Pure ALOHA is clear now. So until next time, adios.